I have here a very simple motor. I got the design off of SciToys.com. And as you can see, it's a 9-volt battery, some wire, a coil of wire, which looks a little bit different than the other wire. It's painted red, and a magnet, which is taped to the playing card. It doesn't look all that interesting, but when I give the loop of wire a little kick, it keeps going. And it's actually acting as a tiny little electric motor. The chemical energy of the battery is being converted into kinetic energy. And it has something to do with the magnet. There's a lot you can learn from this little motor, and this video is going to attempt to explain some of it. First important thing to understand is that the space where the coil is affected by that magnet. I've got my compass. As I bring it in, you can see the needle's pointing down. So essentially in the location of that motor, there's a vertical magnetic field running into the table. And that's going to affect what's going on and what forces are on this motor. Because the motor is turning in a clockwise direction, the top is going away from the camera here, the bottom's coming towards it. That means there must be a force on the top of the wire going away and on the bottom of the wire coming towards. And let's try to figure out why that's happening. So I'm going to disconnect the battery. We'll take a look at the motor. As you can see, most of the wire is copper colored, but the coil is red. And that's because the coil's been painted with an insulating paint called enamel. If we spin the motor, you can see that half of the enamel's been rubbed away, but the other half is still there. And that means that when the motor's like this, the copper wires are touching and electricity's flowing. But it's when it's like this, the supports are touching the paint and electricity is not flowing. So in this state, it's actually turned off. But when I flip it over, it turns on. So our motor's only on for half the time. And that's kind of interesting. Let's take a look at what happens if I add in a different coil of wire. One where I've scraped the insulation off of all sides. So here I've got the same setup, but I've got that other coil of wire that has all the insulation stripped off. I'm going to hook up the battery and watch what happens. It's definitely a magnetic force. It definitely started going, but it's like it's rocking itself back and forth. First it goes one way, then it goes the other way. It doesn't really lead to any sort of net motion. It's almost like the forces are opposing each other. They pull one way, then they pull the other, then back and forth, and nothing happens. And that's exactly what happens. That's why the first coil of wire we had was set up so that the coil turned itself off every half turn. Apparently that's really important to keep the thing moving. And let's try to figure out why. So hopefully this will explain what's going on. I've got my coil of wire, which I've drawn in white. So it's wrapped around like this, and then it goes this way. We saw that the top of it went away from us, so that meant that there was a magnetic force, FB, pulling it back. For some reason, magnetism is B. This side came towards us, so there must have been a magnetic force pulling it forwards. We knew from the compass that the magnetic field was pointing straight down. So we can use the right-hand rule to figure out what direction the charges must have been going through the coil to figure out why it turned the way it did. So if I bring my hand in here, we know the direction of force goes with my thumb. My fingers other than my index finger go with the magnetic field, so they're pointing down. And then my index finger is with the direction of the moving charges. So that means the current must be pointing in the direction of my index finger. So that implies the current on top is in this direction. course, it's a coil of wire, so the current on the bottom must be in this direction. And the right-hand rule says that will produce the forces that we observed. But what happens when the thing turns 180 degrees? Well, the coil of wire isn't being physically altered. So what that means is now up top, this part is now on top, and that means current has kind of switched direction because this part has to match that part. And it would mean that this part has also switched direction. So what's going to happen to the force? It's going to be the opposite. It's going to get pulled this way and that way. Opposite of what we had before. So that's why the motor, with all the insulation off, doesn't work. The forces change every time you go 180 degrees, and they just constantly rock themselves back and forth, and the motor doesn't go anywhere. By stripping off the insulation only on one side, basically we're saying that we're not going to have this situation at all, that we're not going to let current flow through at all. And that means we only have the magnetic force when the current is in this direction, and the thing's just turned off when it's in this direction. So that's why the motor that has half its insulation works. Clearly this is not the most efficient thing, because having your motor turn off for half of its life means that it's not going to be as powerful as it should be. So there must be some sort of better design, and that's what we're going to see next. This device is called a St. Louis motor, and it's a really good representation of how we overcome the problem that the direction of magnetic forces on the current changes as it rotates 180 degrees. Let me unplug it and we'll take a look at what's going on. So in this system, that tan coil wire serves as an electromagnet, and the force is put on this rotating green wire. And if you look at what hooks the electricity up to the green wire, it's these pieces of metal that come out and brush the rotating thing. They're called brushes. If you look, they're touching a very interesting thing that spins. It's broken in the middle. It's got a gap between the two sides of the spinning thing. And what that means is that as the green thing rotates, first one of the brushes is touching and then the other one is. And each of these broken cylinder pieces is hooked up to a different end of the coil of wire. And what that means is that the current switches direction as it goes from one brush to the other brush. And that means that just as the forces change direction on a current carrying wire as it goes in a circle, this is designed to make the current change direction so that the forces are always pointed in the right direction and the motor gets a kick throughout its cycle. So this is the basic design for how all electric motors that run off batteries work. This is the fan in your laptop. This is the remote control car you had when you were a kid. And this is why electric motors eventually die, because this brush setup gets worn out.